our case it is a composite carbon. There could be beryllium window and aluminium window. Is it not? Yeah. Yeah. We use composite carbon because composite carbon is a better material which allows the both low energy as well as high energy carbons. So that's the reason composite, and it is this composite carbon material is very sturdy. So this detector has a nominal efficiency of 50%. And when you talk about a HPGe detector or for any nuclear detector, the important parameters that characterizes is its efficiency. So this has a nominal efficiency of about. So you normally classify the detector in terms of relative efficiency. Previously it used to be relative efficiency because sodium, in comparison sodium iodide, what is the efficiency of this? So sodium iodide was considered to be one time the high efficiency detector, benchmark detector. Then later this came. So you compare the efficiency of HPGe relative to sodium iodide. Subsequently, they started, reporting it as nominal efficiency relative to sodium iodide. Relative is nominal means among a group of detectors, if you measure the efficiency, what is it? That's it. So that is the one parameter. Efficiency is the one parameter which characterizes the detector, important parameter. Second one is the minimum detection level. Of course, you will be calculating the minimum detection level for each of these detectors. You will what is the minimum level you can detect with the minimum level of a gamma active radionuclide. You can detect with this detector. That is another parameter. And the third parameter is background. What is the background of the detector? Suppose because even if there is no source, the detector will give you some count, right? Yeah, some counts. So what is that counting? Because lower the background, better it is. So that's why the detector is provided with the shielding and with advanced electronics. For example, you see this detector this shielding is flushed with nitrogen. You have come across such devices? This is nitrogen being flushed inside the cavity of the thing. You see, there is a gap between the detector and shielding. You see here. Detector is there and there is a cavity. This is the gap. Okay. So there we always flush nitrogen. That is because to reduce the background. So normally what happens, this air gap will have radon as well. So this radon is progeny. Yeah, radon progeny will accumulate. That builds up the background. So we don't want that radon to be there. So that's why this nitrogen, the nitrogen in the gas form, liquid gets converted into gas. Mapping ಮಾಡ್ಲಿಕ್ಕೆ ಅದು ಅದಂತ ಹೇಳಿದ್ರೆ ಅದರಲ್ಲಿ ಅವರ ಡ್ರೋನ್ ಅಲ್ಲಿ ತೆಗೆಯುವ area. So that's how you reduce the background. So survey mapping ಅಂತ ಹೇಳ್ತಾರೆ. Relative efficiency ಅದು minimum detection level. Of course minimum detection ಅದರದ ಐಡಿಯಾ ಇಲ್ಲ ನನಗೆ. ನಾನು ಯಾರತ್ರ equipment ಯಾರತ್ರ ಇದೆ ಅಂತ ನೋಡಿಬಿಟ್ಟು ನಾನು ನಿಮಗೆ ಹೇಳ್ಬೇಕು. Of course your electronics. So this is the basic detecting side. Idea. We have electronics too. ಜಾಗದ ವಿಡಿಯೋ ಹೀಗೆ ತೆಗಿಲಿಕ್ಕೆ ಬರುವುದಿಲ್ಲ, ಅದು ಮ್ಯಾಪಿಂಗ್ ಅಂತ ಹೇಳಿ. Talking in detail, and we have 3 high purity germanium and 1 sodium. Of course, he has already said the difference between sodium iodide and high purity germanium. What is that? ಜಾಗ ತೆಗಿಲಿಕ್ಕೆ ಮಾತ್ರವಾ? ನಾನೊಂದು ನಂಬರ್ ಕೊಡ್ತೇನೆ. Resolution. So efficiency of light. And the main is rate ಅಂತೇಳಿ. Resolution is the one which is an important parameter because here ನಾನು ಡ್ರೋನ್ ಇಲ್ಲ, ನಾನು ಡ್ರೋನ್ ಸೇಲ್ ಮಾಡಿ ಸುಮಾರು ಟೈಮ್. 100 isotopes, gamma isotopes. You can determine all of them. Whereas in sodium iodide, you will not be able to distinguish two peaks. Right? Yeah. ಅದರಿಂದ ನಂಗೆ ಒಂದು ಹಾಯ್ ಕಳಿಸಿ. But it has its own advantages which will discuss with you later.
ID card, ನಮ್ಮ
So you
pump
can see
ಅಲ್ಲಿ
this detector spectrum. Some of you show them the uranium thorium spectrum, potassium spectrum.
ಆಂಪಲ್ ಇಂಟ್ ಅಜಯ್ ಕುಮಾರ್ ಅಜಯ್ ಗೊತ್ತಿಲ್ವಾ ನಮ್ಮ
And GARD.
ಸೆಕ್ರೆಟರಿ.
Okay. So as sir said, so we have three high purity and one sodium ion. Now basically I want you have understood basic aspects of this detectors. The background correction. So whatever the detection it is, let us say alpha, beta or gamma, background correction is must. So what is background? So background is a radiation level that is already present in the air. But when it comes to detector, how much of this background gets inside the detector so that it is detectable. So it is same for sample as well as when sample is there also you get background. When without sample also you get something. So we have to subtract. Or else unnecessary some counts will add it up. Unnecessary things will add it up. So, yeah, it is countable. We don't want to count. So we keep an empty.
Yeah.
So for example, if this is my sample, so this is a thorium sample, RGTH. So if I will keep an empty bottle of the same inside and count the background, then I get the background of this plastic bottle as well as environment. So other ways to reduce background is using this shielding. So this shielding is special because you might have seen already. Basically people use brick shielding, right? Lead bricks to shield. But this is molded. So because it is molded, you will get, this is also lead, not lead bricks. Yeah. This is molded. Molten lead is molded into this, and this is 10 centimeters. So because of this, background is very less. So that is why we call it as ultra low background detectors. So background is very much less. So whatever the counts you get, most of it will be there from the sample. Most of the times we get 1 or 2 counts for the sample. So because of this, you can see the minimum detection level. So minimum detection level for cesium in this detector is almost, sometimes we get at about 0.1 becquerel per kg. So 0.1 becquerel per kg, you saw how much is 1 becquerel of cesium. 1 becquerel of cesium is 1 into 10 power minus 13 grams of cesium. So that much small activity we can detect. 1 becquerel is 10 power minus 13.
Direct mic,
0.1 would be again 10 power minus 14. That much minute activity is also detected. Now this is basics about the background. So once we have done that, then there are different types of detectors in HPGe. So you have well type in the sense it will have a hole in the between and 360-degree counter. Then coaxial detector, which only detects one side. Each one has its own advantages that you will learn during the course of this. Yeah. So this is coaxial. That one is well type. So different types we can use. So we use HPGe basically coaxial. So each has its own advantages and disadvantages that we learn slowly. So this session is only to familiarize with the stuff. So now this is HPGe liquid nitrogen. So why do we need liquid nitrogen? You might have already learned why. Why do we have to cool? Yes. So semiconductor, semiconductor behaves as a conductor at room temperature. So how does this an HPGe work? So you basically have a PN junction diode. Okay. So you reverse bias it. When you reverse bias this junction diode, there is a large amount of depletion, large area for depletion region. So when radiation falls on this depletion region, each radiation will correspond to certain amount of current. Okay, an electron hole pair is generated and that will constitute electric current. Okay, that current is then made it into this spectrum. I'll explain how. But if the detector is kept at room temperature, in addition to this count, there is large number of thermal electrons that is generated. That also gives electric current. Now I don't know how to separate these thermal electrons with this. So because of that, we keep it at minus 178 degrees Celsius by using liquid nitrogen. Okay. 169. Sorry, 169. Some say 178. So somewhat around minus 170 degrees Celsius. Okay, that is the temperature of liquid nitrogen. Minus 170 degrees Celsius. Yes.
Or 100 Kelvin.
Yeah, approximately that amount. So this is the need for liquid nitrogen. Oh, this is only required in semiconductor detectors. So you can see that sodium iodide does not have it. The principle over there is completely different. I'll explain after we finish this. Okay. I hope sodium the scintillation detectors has been taken in class, in the last class. Yeah. So now coming from, so I have got a signal. You understood signal is generated, right? Now this signal has to be converted into these peaks. How do you do that? So basically, if for any kind of signal, you need amplifiers, correct? So your amplifier is over here. My amplifier, main amplifier is over here. Now, during the transmission from there to here, using large number of wires, these electric signals are very minute. Okay, very small electric signals are generated by the interaction of radiation with this semiconductor material. Now, while transmitting it from over there to here, generally there will be a lot of other like noises generated in the cable, correct? It will be there. So how do I remove that? What to do for that case? Any idea?
Pre-amplification.
Yes. So we keep a preamplifier here itself, near the detector. So this wire comes from the preamplifier itself. So inside the detector there is an amplifier. As soon as the signal is generated, within the least amount of distance, we amplify it. A small amplifier, yeah.
Some extent.
So to some extent. That is what we call it as preamplifier. So that is then transmitted to this. This is a preamplifier plus MCA. So it has MCA is multi-channel analyzer. Again, that has been covered.
No, they didn't
Oh,
come
okay, yeah. So amplifier. So here we amplify it, and now you have signals. Basically, we have so many signals, each of specific, let us say, current, okay, or specific voltage. You have current, like current by current distinguishing and voltage distinguishing systems. So either one of them is used. So now suppose we have a separate voltage. So now I have to assign, the system has to assign one voltage is equal to 1 keV. So we have, this is 32,000 channels. So 32K MCA. 32,000 boxes are there, digital boxes are there, in which I can assign one box is equal to whatever I need. So we have assigned here one channel is equal to 0.25 keV. That means four channel is equal to 1 keV. Understood? So I can distinguish, that means this system can distinguish between 1.25 keV and 1.5 keV. So 0.25 keV we can resolution is there with the system. So each signal it comes, it will put into different boxes. So whatever the, for example, signal is coming of 100 keV, 10 signal is coming. So it will put into 10 into 100 keV box. This box is not this box, but I am just saying a computer storage unit. Okay. So now let me show it here practically how it looks. So this is a spectrum of uranium. Okay. Yes, this is a spectrum of uranium. Now look at this. See, there is one peak over here. So these are background levels. Okay, these are all background levels. Now I am getting a peak over here. Now let me check what is the peak energy. So when a so we have one peak and there will be small tail to the either side. This will not be a sharp peak like XRD. Have you seen XRD peaks? It is very sharp. This will get a Gaussian curve, because of there will be small amount of activity or small amount of current be put into each other boxes. So now this is 46.5 kilo electron volt. Now I can identify what is, I know 46.5 is generated over here peak. So I can identify what 46.5 is. It is basically lead to tin. Okay. Similarly, then I will take the area of this peak. For example, just pay close attention. This will be taught to you in the class, but I'm just giving you a brief introduction about this. So I can zoom in and zoom out. So this is a, can I say that this is the start of the peak? Can I say that this is the start of the peak? So I'll put a marker over here. Okay, then I'll take the other marker. So this point I have put over here. For your easier understanding, I'll make it into bigger peak. Okay. So I can say this is the start of the peak, or I can say this is the start of peak. Understood? So this one, shall I put it over here? Correct? Okay. So this is our peak area. Okay. This much counts we will take. So this area consists of 80,887 counts. Okay. And that is for 60,000 seconds. Okay. Then using that formula, counts per second is counts net area. This net area divided by the counting time, CPS into 100 by yield of this peak, that is 4.6, I guess. I'm not very sure, I just have to say. Somewhere we get it from literature, into 100 by efficiency that I have already calculated, that we will teach you later how to do. Into 1000 by weight, I'll get weight of the sample, I'll get what is the activity of lead to 10 in this.
How do you identify that this peak is lead to 10?
Yeah, that is what it is given in the literature. I hope sir showed you one library in the morning. Do you remember? In that library, we get we know that this energy corresponds to this peak. Okay, 46.5 is always lead, but sometimes some radionuclides, let us say bismuth 214. Bismuth 214 has 10 peaks, maybe more than that. So many peaks are there. You have 604, you have 1764, you have 352. So many peaks are there. So if either one of the peak is missing, I cannot say that it is bismuth 214. All the peaks should be there. So this is how we identify. Okay. Cobalt 60 has two peaks. 1131 and 1.13 and 1.17. Yeah. So two peaks are there for cobalt. Cesium has only one peak. So using this we can identify what is this peak, and then we calculate, using this we can calculate what is the activity of this peak using the efficiency calculation. How do we do efficiency calculation then? Any idea? You might be already knowing. So how do you do that? So for example, we get any kind of instruments you have used, sir?
So I'm using the RMS only. I do not use this.
No. Any what other instrument you use? UV visible?
No, that are actually mass spectrometers.
You are using mass spectroscopy?
Mass spectrometer.
Which
They
one?
are very low efficiency.
Which one?
Like 1 or 1 only.
Which mass spectroscopy?
Mass spectrometer. These are IRMS.
IRMS. Okay.
Isotope
So it gives elemental concentration?
not elemental. They give the ratio of
Molecular weight.
Molecular weight. Okay. So here, have you used ICP-MS, sir? No. Okay. Or XRD. Okay, XRD might not.
UV visible.
UV visible you have used? Okay. So basically what I am trying to say is that in any kind of spectroscopy analysis, you will get something called as a reference material. So ICP-MS, you have a reference material. It is generated by NIST, National Institute of Standards of Measurement, something like that from USA. They have the reference material. For us, reference materials are usually from IAEA, International Atomic Energy Agency. So this, whatever I showed, is a reference material from there. So they will use the same sample, calculate multiple times for years together, and then they will say that this is a reference material, this is the value. Okay, for this peak, for lead to 10, this is the value. For uranium, this is the value of this peak. Now I keep this sample, I'll take the count, and using the formula, the efficiency is nothing but CPS, that is counts, same counts, into 100 by activity, because it is in percentage, into 100 divided by abundance, yield. I'll get efficiency on percentage of this peak. Okay, that efficiency I'll use in the later stages to count the samples. So that is why while you doing HPGe analysis or sodium iodide gamma spectrometry analysis, your sample geometry and your standard geometry should be same and should have the same density. For example, if you are using standard water standard, or even like if you are using sand standard, and if you are using soil for your analysis, your results will vary largely.
Okay, so you have to standard and sample should be same.
Same. I am saying the density should be same. The material composition should be same. For example, sand should has its own standards. Soil has its own standards. Water has its own standards. Filter.
IEA provide
Yes, yes, yes. You, for vegetation, for example, banana, it is, clover is there, IAA clover leaf is there. Then you have, uh, so spinach is there. Then so many things are there. I can give you a whole list. So we have around 20-25 standards here. So each sample is different for us. So you give us one sample, it is different for us.
So every time you use IEA standard also?
Yeah. Sample density and your standard density should be comparable if it is not same. I cannot use water standard and then use a soil standard for counting. Yeah.
So every time you use IEA standard, or you have the laboratory standard?
We always use IAA standard. We don't compromise on that. So we have IAA.
So similarly in mass spectrometer also, for we are doing the stable isotope for water. So we also have the IEA standard.
Oh, okay.
But then we prepare the lab standard comparing this IEA standard because
Okay.
they are very expensive.
Okay, but no, IAA is free. IAA standard for us is free. No, for all the radioactive measurements, it is free if it is available. Only shipping charge is what we have to pay. So that is what I know, but maybe it might be different for different cases. Maybe it might be different. So we use, like we have standards from 1990s onwards. So from here, whatever the standard that comes, sir has bought it. So we don't have to worry. And every year we participate in something called as international interlaboratory exercise, that intercomparison exercise and all. So for using, they send us samples and all this. So you might be knowing. Yeah. So because of that, we can say that our results are standard. So this is all about HPG. Any doubts?
How activity is completed?
See, you take the peak, you get the counts, net area. You can see the area. So this net area is the addition of all the peaks. So here you get counts is 2579. Can you see here? So this peak. So next channel 459, channel number 459 gives you 2847. Next channel 460, 3218. Addition of all this will be there in this area which I have selected.
So other peaks are, what elements are other peaks?
So other peaks. So these peaks we don't identify. This peak also we can identify, but I go for very prominent peaks of it because see here these peaks are so close together. So if I analyze, for example, here you get a 63 peak which is of uranium. Okay, I think thorium 234's daughter should be, it should be something over there, but I don't use this because there is like lot of interference, spectral interference, especially over here. See this peak, I don't know whether it has ended or it has spilled into the next adjacent peak. So instead of that, I go for the very well separated peaks. So this is 186 is of radium 226 and this one 242 is I think lead 214 if I am not wrong, but yeah. Oh, no, 241 is another lead. Lead has so many isotopes, so many peaks. So again, this is 295 is again lead 214. So many peaks are there. So I can use any one of the peaks. So for the best results, what we do is that we analyze 4 to 5 peaks and see whether the results are comparable and take the mean and give the standard deviation. So that standard deviation will be 1 sigma. We can give up to 2 sigma. 2 sigma levels we can give. That is 1 sigma is 1 standard deviation, 2 sigma is multiplied.
Activity of all the isotopes or only uranium? How do you give the results?
So for example, you are an user, you will say that I want only lead. I would not look at any other peaks. I will only give you lead. Suppose if you are asking for cesium, I will give you only cesium. But if a user asks me, give me K40, give me thorium activity, give me uranium activity. Uranium in the sense we cannot, you might be already knowing, uranium we cannot identify using HPGe. What we do is that we keep a sample, pack it and keep it for 28 days like this. So that time what happens is that radium and its daughters will come in equilibrium. Okay. So then its daughters, bismuth 214 and lead 214 peaks we will get. That using that we will give you radium 226 results. Yes. So radium 226 results we will give you. We don't know radium 226 is in equilibrium with uranium. If it is in equilibrium with uranium, then both are same. but we don't know that. We cannot establish that. So we don't give you uranium 238 results in HPGe. We basically say it is radium 226 results. Okay, that we can give. That peaks are there. So radium 226 again, bismuth 214, lead 214. You can understand. So this is just an introduction. Basically, in after like in a second session or third session, you will have to do this. That time you will understand. Okay, then you can get cesium 136. These are all naturally like cesium 137. Naturally, like what are being asked by us so far. So you can also if you go for the like nuclear installations, there they will analyze americium 241.
I'm not that keen
Okay,
on to detect.
they have
They
another
also
other
do the same
yeah,
thing only, K40, uranium 238,
and thorium,
and
yeah,
one more I think, thorium and
cesium 137 you do.
three, four isotopes I remember.
Yeah, lead you won't get in sodium iodide.
No, they also have HPGe.
Okay, but yes, if they have an HPG, if it is a carbon window, you get that peak. If it is not a carbon window, you will not get that peak. So yeah, so basically this is it. So any other questions? So if there is no questions, we can go to sodium iodide. Okay, I hope this is clear. Introduction wise, this is clear.
Can you just keep one sample and acquire and show?
It will take long time, ma'am. It is like 30,000 seconds. This is 60,000 seconds counting time.
Full day?
So yeah.
You can keep that cobalt 60 or 60, that microgrid samples.
Yeah, we can give you. So this is already counted. So we keep the sample inside, the same sample, something like that. Soil samples we keep inside, we close it, and we give count. Tomorrow morning it will be counted. That's it. I don't have to do anything else.
That you are not even the reference samples, cobalt 60 or 60.
We have. So that is a reference material. That is for the reference material. You mean say that disk that is also there, but that is very high active. Yeah, it is like we have 38 kilobecquerel active.
30 kilobecquerel high active.
For us, environmental samples. So we say that like anything over than 1,001 kilobecquerel for us it is.
Microgrid level.
Yeah, microcurie level it is okay, but I don't keep. So if yeah, the dead time will be more in that time. No, we can keep. I can show you. That is not a big deal. Maybe tomorrow or day after tomorrow I can show you if there is time. That is not a deal.
Sampling price, how much?
This one per sample we charge 2,000 rupees in HPG. Okay. Because the main cost goes to liquid nitrogen. Liquid nitrogen is very costly in the sense every week we need around for 3 HPGs we need 100 liters of liquid nitrogen. Approximately. 1 liter costs around 40 to 45 rupees, or sometimes even it goes to 55 from outside. So that is what. So cost goes to maintenance of the instruments. And all those. 1 liter is approximately 50 rupees. We can say 50 rupees per liter. So 100 rupees, 100 liters per week. So yeah.
No, some are P-type, some are N-type.
Yeah.
Choice.
That is depending upon how you want. It does not make a very much difference. So when we are buying, for example, when you are buying one detector, we mainly see about that nominal efficiency, what's your told, how much efficient it is. So now you have 100% efficient detector. That means 100% of what sodium iodide is giving, that it will give. So always previously they used to say relative efficiency. So relatively that was the thing. Efficiency was mainly seen, but this P-type and N-type will not make a huge difference as a user. But cost-wise, I don't know.
N-type is very costly.
N-type might be costly, yeah.
N-type is used for X-ray detection.
Which one?
Planar detector, X-ray detection.
Yeah. Okay, maybe I'm not very sure. Okay, then, yeah. Done? അത് അവരെ കാട്ടിലുണ്ട് അത് ഓക്കെ അവൾ ആടെ കൊന്നിട്ടുണ്ട് കാർട്ട് എടുക്കണം അവളുണ്ട് ഓക്കെ സോ നൗ
Relative efficiency. 3/3 sodium. That is the
just give me a second.
activity.
Pause one play. So in this you can see the electronics clearly. So here we have the high voltage power supply. Okay, this is the amplifier, this is the MCA, multi-channel analyzer. So all three are different. So this voltage we have supplied is 4 kV, 4 kilovolt. That around 4.5 kilovolt. This one is minus 3.5 kilovolt. Okay, so this is a spectrum similar. No. This is N type. Those two are negative charge. Yeah, is having less resolution and more efficiency. Efficiency of sodium iodide is more. So you can see that. So still it will give you a very good result. But for example, okay, the same sample, uranium sample. Okay. Yes. So it's loading. It's taking some time. Yes, okay. So you can see that. So I have preloaded ROIs, ROI in the sense region of interest. So I have bismuth 2. So you can see that, yeah. So this is a bismuth 2 for peak. This is 609 keV. So you can see that you are getting one peak over here. Okay. So you can see that in there the same sample. You can see the spectrum has so many peaks. Correct, but here you have only countable 1, 2, 3, 4, 5 peaks. So the efficiency, although it is higher, or if I do better resolution, even then. So here the first peak I am taking is of 609 bismuth peak. You might be already knowing that. Beyond that you don't use. There I can start from 46.5. Here I will start from 609. So prior to that, all the peak I am just leaving. I just don't count it. So from here onwards, you have this is 795, I guess, and then this is one more peak. So basically, and one more thing. Okay, can you see any other differences between this and that? Something based on spectrum. Look at this. Background is different. Something else. Resolution, yeah, and resolution we already know. Something else, see some differences there between that spectrum and this spectrum. Just looking at the spectrum.
Less peaks. Peaks are less.
Peaks are, that is resolution. No. Look at this curve. This is Compton effect. So this is a Compton scattering. So this peaks. So this is, for example, this one is thallium 208 peak over here, which is not present in the sample. That will contribute to the previous peak. So there is some contribution of present. If there is a thallium 208, it will contribute some activity to its previous peak, that is bismuth 214. Now again, K40 peaks count will be, there will be some contribution from thallium and also bismuth. So additional peaks will have the peaks which are in front of the higher energy peaks will always contribute to the lower energy peaks. So we have to make a separate calculation to suppress this. Okay, there that issue is not there. Their Compton correction is done by the PC itself, done by the software. I don't have to worry about Compton correction. Here we have to do Compton correction. Okay, and again this is a scintillation detector. Working is different. There is a 3x3 sodium iodide crystal, thallium doped. So their electrical signals is generated by the reverse biased diode. Here, because scintillations are produced when the radiation falls on this material. Scintillation means flashes of light. So that is then converted into electrons by a photocathode. That electrons are then multiplied by a photomultiplier tube. Then that final counts are taken, and then we get a spectrum like this. Okay, so this is all about sodium iodide and high purity germanium detector. Any questions you can ask?
So this is well type.
This is well type. You want to see it? So I have kept a sample here. So this is the well over here. Can you see that? This There is a hole.
Okay. So how
This is a fan. So I can either keep the sample on top of it, or if I have a very small sample of this diameter, I can keep inside it. Okay. 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 Yeah. Okay, that's it. Any doubts? Any questions? No? So if there are no questions, I assume you have understood everything, or I can assume you have not understood anything. So I assume that you have understood everything. So if you have not, please come and ask at any point of time. I will be here, or you can ask anyone among us. Okay? Okay, sir. Then can we move to the next lab? Yeah. Yeah. Yeah, fine. The questions not only raises increase our knowledge also. Sometimes some questions will make us think a lot. We also might not be knowing some minute details. Sometimes some visitors ask, and then we'll think, oh, this can be thought like this too. So yeah. So that is why questions are important for both of us. Yes, then we can move to the next lab. Okay. Thank you. Thanks a lot. Yeah. You have a question?
It's a radium, 186 is a radium peak. We measure the daughter product.
But we don't measure 186. 186 is not always present. Yes, sir.
This is equal to activity of daughter
ಆಗುತ್ತೆ
equal ಬರ್ಬೇಕಲ್ಲ.
ಬರಬೇಕು ಬರಲೇಬೇಕು ಬಟ್ 186 ಯಾ
So honest, I have never used this kind of instrument.
ಓಕೆ
So I have so many basic questions.
ಯು ಆರ್ ಇಜರಿ ತೊಂದರೆ ಇಜಿ so yeah, so you have you are coming from alpha and beta. So you have seen alpha and beta measurements, right? So both places you have to do some kind of sample preparation, right? There should be some kind of digestion, some kind of conversion. So this is mainly because of their penetration. So alpha and beta are least penetrative. So we call these methods as destructive techniques. Okay. So those are destructive techniques. So once the sample is analyzed, it is lost. You will never get it back. But there is another type. Easiest of all the three, easiest way to measure radioactive element in a sample is by gamma spectroscopy or gamma spectrometry. The reason being, it is highly penetrative. You don't have to like use any kind of methods to calculate its activity. So for example, tomorrow you bring one sample to me. I don't have to break it, or I don't have to digest it. I can put it into a certain bottle, and I can keep, I can count, I will get the result. After the counting, I can give back to you. So now we will understand how this works and what is the main methods that we use, and how you can also basically basics of these detectors. Okay, so in this lab, look around and see if you can identify the types of detectors. Can you please look around and see what are the detectors available over here? No. How many?
One HPGe.
Wrong. It's the other way around. So we basically have 3 HPGe and 1 sodium iodide. So the easiest way to identify a HPGe is that HPGe will always have a liquid nitrogen cylinder with it. At most of the cases, unless it is very advanced HPGes have electronic cooling, but again, it will have something below. Sodium iodide will not have anything. So yeah, so this is HPGe, one of the HPGes. There is one more HPGe over there. There is one more HPGe over there, and this is a sodium iodide detector. So that HPGe is around 22 years old. That one is again, it was procured in the year 2008. This one is the latest procured almost 10 years back. It's 2015. Okay. So now let us see Why gamma spectroscopy, gamma spectrometry? So as you have learnt in the classes, so when an alpha and beta decay happens, the daughter product, daughter radionuclide might not always go into the ground state energy and might be in the excited state, and from there it might emit, it will emit a gamma or X-ray or any Auger electrons to come to the ground state. That gamma is what we are identifying here. So not all, when this process happens, not all the like let us say if there are 100 atoms, for example, if I take the case of cesium, not all the 100 cesium will give this 661 the gamma peak. So 5% will go directly, 95% will go to the excited state. So of that 95%, only of the 100, total 100, only 85.4% of the particles will give you the cesium peak, the 661 peak. That is, it will emit that 661.6 keV of gamma. So this is what we spoke about the yield in the earlier classes. So now, can you please move back? I will show this detector. So this is our HPGe. So let me start with whatever is the physical appearance of this HPGe. So basically, you can see that there is a big shielding over here. So this shielding is kept in order to reduce the background noises. For example, you are going to learn, unlike our popular assumption that radiation is not available everywhere. Radiation is like radionuclides are available in the air we breathe, in the water we drink, in the soil we live on. So these radionuclides, maybe from cosmogenical sources, from terrestrial sources, will interact with the detector if I keep it open. Right? So I'll have to reduce the interaction of this radionuclides that is not required in the counting process. So we have kept a 10 centimeter thick lead shielding over here. So you can see how thick it is. So this thick lead shielding, and then you have the detector under this. So this tissue paper is kept to remove any kind of particles that fall into it. So you can see that that is the.
Keep sample on top of this.
Yes, we keep the sample on top of this one. This is again another protective cover. So the main thing is that there should not be any kind of dust particle falling into it. So we will have to always keep the tissue, and below that there is the detector. Okay, is it done? Yeah. So now, so that is why we keep it always closed. So because suppose what will happen if there is some kind of dust particle inside?
That also come into the.
Yes. So background increases. So if background increases, there is another parameter that increases, that I'll tell you later. So from that detector, so you have seen the detector. This detector, HPGe, the name says that high purity germanium. So germanium is a semiconductor material. So how do you convert this semiconductor material into a detector? So how does a semiconductor? Semiconductor is nothing but a PN junction diode. That is what we are having here. So we reverse bias it. Okay. So when you reverse bias it, what happens? There is a large area of depletion region that is created. So when your sample has some radiation sources, radionuclides, it falls on this depletion region, there is an electron hole pair is generated. Okay. So that means a current is generated. So that current is what we get here as peaks. I will tell how it happens. Now, can you tell me the rationale behind keeping a liquid nitrogen, this detector immersed in liquid nitrogen? With the information you have got now.
Maintain the temperature.
Why should I maintain the temperature, sir?
Create a depletion region.
No. Yes, sir. Ah, yes, sir.
So the temperature increase actually the pulse noise.
Yes. So semiconductor is very sensitive to temperature changes. So if I keep it in room temperature, lot of thermal electrons can be generated. That will contribute to your signal. Then you cannot distinguish between what is your signal, what is your noise. Or so that is why we have to maintain a constant temperature. That too, we have to, so semiconductor acts as a semiconductor, we know that it acts like a conductor in a room temperature, and it works as an insulator at 0 degree Kelvin. Yeah, so that is why we keep it in a liquid nitrogen. Liquid nitrogen temperature is around minus 170 degrees Celsius, so 169 to be preferred. So to be precise, so we use liquid nitrogen in order to suppress these all thermal neutrons, thermal electrons.
Is it circulating inside?
No, sir, that I will tell you. I will tell you how. So now the signal is generated. That signal is transferred through the cables to this box over here. So this is called as an amplifier. I'll explain in detail over there. So amplifier plus a multi-channel analyzer. Okay, so amplification happens here. Now think about it. The current generated over is very small, and while transferring from there to here using cables, wouldn't be there any noise? There will be lots of noise. So I have to remove this noise. What should I do? Any idea?
You have to increase the
Signal pulse and remove the noise. So for that, we add a preamplifier embedded in the detector. Okay. So there is a preamplifier over there. So that preamplifier amplifies the signal, and then that is transferred to this main amplifier. Okay. From there it goes to multi-channel analyzer. So what is this multi-channel analyzer? So think about, so it has an electronic circuit where there is a lot of spaces. Let us assume that there are so many boxes, and each box I will assume that for example, one box I'll say that this box if any radiation of 0 to 1 keV comes, it should go to this box, box number 1. Second box is from 1 to 2 keV. Third box is 2 to 3 keV, so on. So each box will be assigned specific energy. So whenever the signal, so amplified signal comes, according to its energy, it will put it into these boxes. There are no boxes inside, but I'm just saying. So there are lots of boxes. Okay. Now that boxes or that spectrum is viewed over here. Okay. So for example, now I'll show you from the beginning. So this is our starting peak. So this is 326 channel. So it corresponds to 32.6 kilo electron volt. So next channel is 327, which corresponds to 32.7 kilo electron volt. So my one channel is 0.1 kilo electron volt. So every 0.1, if there is an energy difference between 0.1, still it can resolute and put into different channels. Okay. So now how a peak is generated? How this peak comes? Okay, so let us go to the first peak over here. So I'll identify what the peak is. So we will put a cursor on the top of this peak. So peak value is, peak channel number is 46.8 kilo electron volt. Actually this should have been, there will be slight shift here and there. This peak is 46.5 kilo electron volt, which is of lead 210. Okay,
Binding energy, sir?
What binding energy?
Sorry. Before getting that peak, sir, some other peaks are there. That means
see this peak before the whatever the lower peaks is not observed in this HPGe. So high purity germanium detector, the it depends upon your carbon window. So the window. So we have a carbon window which can start detecting from 30 kilo electron volt. Okay, and then if you have an aluminum window, I think, sir, it is 100 keV, aluminum, yeah, something like that. And then there is another composite window, again it will give some other energy. So we have the best one, that is carbon window, which will start counting from 30 kilo electron volt. So anything below that you cannot detect by HPGe, at least by this HPGe. I don't know if there is any other HPGe that can detect lower than that. Okay, now, and again, that those from 30 to 46.5, this sample, this is an uranium source. It does not have that peak. So there is no uranium radionuclide daughter of uranium that is giving a peak between 30 to 46.5. 46.5 is the first peak, that is lead 210. Okay. Now, as I said, if I come to the one end of the peak, see, I'll zoom this area, single peak, we will zoom it. Okay, this I will take as my start of the peak. Will you agree? This point, this point, this point. No? Then which one will you take? Slightly further, over here. Okay, you can take that. Now, wait. You said over here, right? Now this one is the starting of the peak, right? Okay, I will take that one. So this is the start of my peak, and this one is the end of my peak. Will you agree? Little bit this side. Okay. Over here. Will you agree? Okay. Now, see this channel over here, this channel 45 point, so no, not that. Yeah, 45.6. It has counts of 2368. Okay, this channel, this one channel. The next channel over here has counts of 2463. So on, so on, so on, so on, so on, so on. You have 9,000, 10,000, again 9,000. 46.8 has a peak energy of 10,250. Now, for me to identify how much activity of lead 210 is present, I want the whole count of this peak. Okay, so that is given. I have marked two areas. This is my starting marker. This is my left marker. This is my right marker, and I'll see that total counts under this area is 78,378. That means total of this whole area contains 78,378 counts.
Centroid,
Centroid is that one, 46.8.
6.8.
Yeah. So that is the lead to 10 counts in this sample. Now, what is my counting time? Counting time is 60,000 seconds.
60,000.
So counts per second is calculated by
Parameter is same for all.
what
That
parameter?
60,000.
No, it depends. I can set it like 30,000. If I want, if the activity is high, I can set 10,000, 5,000, even 1,000, 100 seconds.
You set instead of 60, 10,000
You might not get this big peak.
big peak.
You might
Is
get
there any difference with respect to that the centroid?
no.
It might be same.
It might be the same, but you have to get a proper peak. So, for example, I'll show you. So this is counted for 40,000. Show me a peak.
Less time, less count will be count.
There is no peak. This count does not have any peak. So this is a low active sample. This does not have lead to 10 peak over there. This does not have any peak other than what? See, you have only one peak over here. This is 511.2. That is not a peak from the sample. This is a annihilation. Annihilation peak. So then you have one peak over, the only peak over here is K40 peak. Okay, so if I count this sample for maybe, I can experiment, I can start counting this for 1 lakh seconds, 1,50,000 seconds. Even if there is small activity, it might get detected. So counting, radiation counting depends upon time, distance and shielding. So you can increase the time, you can reduce the shielding in the sense, shielding between the detector and the sample, and distance. So distance, it is 0. I have not kept any distance between the, I cannot reduce the distance. I cannot reduce the shielding because there is no shielding. So I can only increase the time of counting to get the maximum counts. Okay. So that's about these things. And okay, so once I get the total counts, so total counts I have got over there 76,000 something. I divide it by the time, counting time, to get counts per second, CPS. Yeah.
If we change the time, you are saying that 60,000 seconds. What about the HV?
It will not change. It is set.
Set.
Yeah.
Okay. If we what is the HV for present?
4.5 kilo electron volt.
4.5
4.5 kilovolt.
kilovolt.
Yeah.
Okay. Energy level time only change ಆಗ್ತಲ್ಲ ನಾನು ಅಪ್ಲೈಡ್ ವೋಲ್ಟೇಜ್ ಏನು ಚೇಂಜಸ್ ಮಾಡ್ತಾರೆ
ಏನು ಮಾಡಲ್ಲ. It is all fixed. There is no other parameter that we can change. Only parameter I can change is time.
Only time.
Yes, I cannot change the voltage. If I change the voltage, the spectrum shifts.
Okay, spectrum will be shifted.
Yeah.
Spectrum will be shifted. Either that is lower side or higher higher peaks.
Yeah.
According to that peaks, you are setting your timing.
No, 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 no. Once you set your high voltage, you will not change it at all.
Okay.
So if you change your high voltage, your spectrum gets shifted.
Shifted. Okay.
So you don't want your spectrum to shifted. Your energy calibration will go wrong. So for example, if this peak comes at over here, let us then I cannot say this is lead.
Lead. Okay.
This lead 210 peak, if it comes here, I can say that it is uranium. So I don't want this peak to shifted. So once I set the high voltage, I will never change it.
High voltage is the operating voltage given to the detector. Okay. So each detector will have a designed high voltage, operating voltage. Once it is set, it is done. You are not going to change this daily. So, for example, if I start the switch on the detector today, I set the detector voltage at 4,500 volts today. That's it. You are not playing with that again. Then you are only collecting the data with the detector. You daily change the sample, acquire the spectrum.
When it switch off, again we can do.
When you switch off,
again we can
you reduce it to 0
Okay.
and then switch off. And then you after 2 days you switch on, you again set it to 4,500. Like that.
Okay. So once we got the counts, they count the activity, as I said, using the formula CPS into 100 by the yield of the peak into 100 by the efficiency. So now we have another factor over here, which is efficiency. So we have to calculate efficiency. How do we do that?
That we can is about the calculation method. We there do that.
Okay.
Now today you limit your explanation. What is the system? Gamma spectrum.
Okay.
There is a detector. Detector is maintained liquid nitrogen, and there is a spectrum analysis
Yes.
hardware and software.
Yes, sir.
Okay.
That much is done. Yeah. So then.
And then about the procedure, how to count the sample, how to take the counts under ROE, and how to determine the efficiency, how to subtract the background, and how to calculate the activity, we will demonstrate tomorrow.
Okay, sir. Yeah. So this is about HPGe.
Right.
Yeah. So this is about HPGe. Any doubt about HPGe now? Okay. So yeah, then we can go to the sodium iodide detector. So the same spectrum, whatever I have, same sample which I have kept over there, I am showing it here. But before going to the spectrum, we will just I'll just explain about the system. So there you had a semiconductor detector, right? Semiconductor detector, we reverse biased it and all those things I have explained. So can you go a little bit back? Yeah. So this system is a scintillation detector. Okay, this is a sodium iodide crystal, which is doped with thallium. Okay, thallium doped sodium iodide crystal, which is kept inside this. This is a well type detector. Okay. So now, what is the difference between this and that? Is that yes, sir?
After you finish this batch,
Huh?
let them go for tea.
Okay.
We give them 10-15 minutes gap
Okay, sir.
for a break for tea.
Then
we'll resume.
okay, sir. Yeah. So now the main difference between this and that is that here, after the sample will when the radiation falls on this crystal, scintillation is produced. That sparks of light. Yeah, not spark, like scintillations of light. Scintillations of light is produced. This one, once this is directly the intensity of the scintillation is directly proportional to the incident of energy. Now, one scintillation photon, we have to convert it into electron for counting to get as a signal. So that is converted into electron using a no before that no before that photosensitive. No, before photomultiplier tube there is something. Cathode. So there is a photocathode that converts this photon into electron. That electron, that is single electron, is multiplied using photomultiplier tubes. One is converted into 2 is to 4, 4 into 8, so much, 2 to the power n times we multiply it, and then the same system continues. You have, see, I told you the high voltage power supply, this is the amplifier, and then you have a multi-channel analyzer. So first high voltage will go to the detector, from there it comes to the amplifier, preamplifier is already inside, Then amplifier, from amplifier it goes to a multi-channel analyzer. So then the spectrum is obtained. Same thing. Now,
Which
can,
software sir it is?
this is Genie 2000. Okay. Now, what is the difference between this and that? Sodium iodide. Yes, resolution is poor. Their resolution is good, which is having higher efficiency. This HB sodium iodide is having higher efficiency. Any other difference can you see between that spectrum and this spectrum? That is what resolution is. Resolution is. Anything else? Look at that peak. Look at this peak. See something is different. No, that is zoomed in. That is not. There is some difference. This is basically the same peak, same sample. Uranium I have kept over there. Uranium I have kept over here. I have counted. That's it.
Energy level overlapping.
That is there. Anything else? Anything else that you can look at the peak? So can you see this? There is a slope over here. So this is actually Compton effect. Okay. So this peak, their Compton correction will be done by the Compton correction. I'll explain. Wait. So Compton correction is done by the system itself. The total count you get is Compton corrected count. Here, however, this peak, whatever, this is thallium 171. So this is the bismuth 214 peak. This peak energy, it will contribute. This will contribute some activity to the peak before it. So led to so K40 will be affected by the presence of bismuth 214 or thallium 208. So we have to correct it. So Compton correction, there is some formula that we'll learn later. So that is what there is a Compton corrected peak. This is not corrected peak. That's it. I hope.
How many channels do you have?
This system is 16K, 16,000. That system is 32,000. So that is 16,000. That is 60,000. But here we have limited it to 1,000.
We use 8.
Yeah. So this 16,000 for sodium iodide we have limited to 1,000 channels because resolution is anywhere poor. So it's better to have it at 1,000 channels. So, but 32K will give you a much better resolution. Yeah. Yes.
Size of this size of
That is 3 by 3.
3 by 3.
3 by 3 crystal sodium. Okay, so this is a well type. There is different types of detectors comes. You have coaxial, you have planar. So our HPGs are coaxial detectors, and this one is a well type detector. So the advantage of well type detector is it can detect 360 degree. Okay, you can keep a sample inside it.
Okay, so if we increase the size of the detector, can you differentiate between the?
We cannot, like, I cannot increase the size of the detector as per.
You cannot
Yeah,
increase it.
but
If
yeah,
you use a
I'll tell you.
4
Yeah,
by 4 or 5 by 5,
then efficiency will increase.
efficiency will increase.
Right? Am
In
I
our
right?
laboratory, we have 4 by 4 NITI.
Okay. So efficiency would be good, I assume. I'm not wrong. Am I wrong?
So efficiency.
No, he said that what if we use a bigger detector instead of 3 by 3? If I use a 4 by 4 detector,
whether efficiency will change? Same.
it will increase, right?
Yeah.
Counting area will increase, so more surface area for detection, I guess.
I have one question. How often do you measure the backlog?
Sir, every 15 days. So yeah, every 15 days.
How long is the backlog?
So for HPG, we measure it for 60,000 seconds, or sometimes even 82,000 seconds. That is basically 1 day. This one 10,000 seconds because I count the sample for 10,000 seconds. So background and sample I keep it for the same time.
Standard calibration, standard.
It is all from IAEA. Thorium 232. Geometry, various geometry. We have all most of like different geometries. For example, you give me a sample in a box, like a square box, then we have square geometry. But mainly use this kind of geometry, wide mouth. This geometry we use for because this we have thorium and uranium standards in this. We also have IAEA.
You cannot.
No, it is not available now. RGA is not available.
I'm writing standard. Same only, look like white color only.
Yeah, it is white color.
That's also white color only. So PRC certificate. Uram thora potassium also.
Which one?
PRC.
Okay.
What I recently certificate.
Okay.
Standard, IRMK is like example.
Okay.
Use zircon.
Okay.
Zircon that's it's contained 300 ppm uranium.
Okay.
So there is a zircon is used for the standard for the uranium.
Okay.
And the monoxide contain around
That is used to-
300
yeah.
becquerel thorium. So this monoxide is used for the
Thorium.
thorium.
Okay.
So you submit the sample
BRs.
certificate for
Okay.
distribution with the all HP unit.
Okay.
And the
But
ERC.
this one we procured from IAEA long back. So we have geometries, various other geometries also. We have water bottle geometry for water samples. We have this small geometry for well type samples. We have various geometries.
Procure from IAEA, no problem, sir. In calibration,
Calibration, no. Once you
I am taking about this calibration of standard.
calibration of standard is if that is difficult, yeah. Yeah. So calibration once,
There's a calibration, no problem.
yeah, standard calibration.
Maintenance, AMC, everything.
No,
Standard.
standard calibration you can do one simple thing is that you can keep the same, you have a IAEA standard or any certified standard, you measure the efficiency, then you keep your sample maybe 10, 15 types and calculate the calculation.
No. You are using one standard. You are preparing, you are using the one standard.
Yeah.
So other people are not accepting.
That is what,
So that is a problem. The
Yes.
standard is universally accepted.
accepted,
for
yes.
everyone.
Yes. Okay, then any questions?
No, sir. Thank you.
Yeah. So I think we can take a break
Sir,
for
இது
tea.
எந்த வருஷம் procure பண்ணது?
This is, I think, 2015, I guess, yeah, 2015. Yeah.
All this latest,
That is 2005, not 2003.
அது German. Actually, sodium iodide.
This is also from Canberra.
Canberra,
All,
2015 as well.
yes. Everything is from Canberra. Okay. Yes, I think we can take a break.
Okay, thank you.
Thank you.